Hello everyone and welcome to this video on section 2.8, which is all about the intermediate value theorem. Essentially what the intermediate value theorem says is a continuous function can't skip values. So here's what I mean by that. Let's say we have a continuous function where f of 1 is 1 and f of 3 is 3. So something like this, some continuous function. It can act really crazy. The important part is if there is a point where the output is 1 and there's a point where the output is 3, then that means somewhere there's a point where the output is 2. We can't skip values. If we go from 1 to 3, we have to go through 2, somewhere in the middle. The formal, rigorous mathematical definition is as follows. Definition, or I guess theorem. If f is a continuous function on a closed interval AB, so it's continuous on this closed interval, then for every value m between f of a and f of b, there exists a c in the closed interval from a to b. If you're not familiar with this notation, it just means that c is in a to b, it's in that interval. So there's a c in a to b such that f of c equals m. So this value m is between f of a and f of b. There must be a point between a and b whose output is m. Okay, so let's see this in practice. Let's take a look at an example. We're going to prove that sine of x equals 0.3 has at least one solution in the interval from 0 to pi over 2. All right, so what do we know? We know sine of x is continuous, and so we can probably use the intermediate value theorem, or the IVT as they call it. So first, let's observe that sine of 0 is 0. And also, we can notice that sine of pi over 2 is 1. And that means, by the intermediate value theorem, there is a point between 0 and pi over 2 whose output is 0.3. Because 0.3 is between 0 and 1, we have to go through every value between 0 and 1. In fact, let me pull up a graph right quick. So here is a graph of sine of x. Here's the line y equals 0.3. Let me change this so we can see our steps in pi. So between 0 and pi over 2, the output of this sine function at 0 is 0. The output of this sine at pi over 2 is 1. So there has to be a point somewhere in here whose output is 0.3, right there. So that's how the IVT works. One really cool thing about the intermediate value theorem is that we can use it to find zeros of a function. So we can use the IVT to show the existence of zeros. And when I say the existence of a zero, that means i.e. a place where f of x equals 0. Okay, so let's take a look at a kind of complicated function. Let's say f of x is cosine squared x minus 2 sine x over 4. Okay, and we want to show that this function, show f of x, has a 0 in the interval 0 to pi. So this interval here, this is possible x values. We want to show that one of the y values is 0. So there's a number in this interval whose y value is 0. Well, let's check the endpoints. F of 0 is cosine squared of 0 minus 2 sine 0. All right, so cosine of 0, if we remember our unit circle, cosine of 0 is 1. We square that, we get 1. Sine of 0 is 0. We multiply that by 2, we get 0. So f of 0 is 1. What about f of pi? F of pi, we get cosine squared pi minus 2 sine pi over 4. All right. So cosine squared pi, cosine of pi is minus 1. We square it, we get 1. Minus 2 times, and then if we remember what sine of pi over 4 is, it's going to be square root of 2 over 2. We just know that from the unit circle. So this is going to give us 1 minus square root of 2 over, 1 minus square root of 2, because those cancel out. And you might not know what square root of 2 is, but it is bigger than 1. So 1 minus square root of 2 is less than 0. I don't know what it is off the top of my head, but I know that it is less than 0. So that means at 0, f of 0 is 1, right? So f of 0 is bigger than 0. F of pi is less than 0. And that means there has to be a point. Thus, we can definitively conclude f of x has a 0 in the interval from 0 to pi. Visually, what does this graph look like? Let me type this up right quick. F of x equals cosine squared of x minus 2 sine of x over 4. So it's kind of a weird, wavy looking function, right? But at 0, the output is 1. At x equals pi, the output is something like minus 0.417, somewhere in that neighborhood. Because we start bigger than 0 at x equals 0, and we end smaller than 0 at x equals pi, that means there had to be a place in between where we crossed y equals 0. So that's using the intermediate value theorem to find zeros. It's a pretty nifty application. We can also use the intermediate value theorem to find fixed points. Okay, what do I mean by a fixed point? So we're going to use the IVT to find fixed points. A fixed point happens where f of c equals c. Where you plug a number in, you get that same number back. So for example, in the function f of x equals x squared, we have that the number 1 is a fixed point, because f of 1 is 1. Okay, but how can we use the IVT to find fixed points? Okay, let's take a look at an example. Let's show that the function cosine of x has a fixed point in the interval from 0 to 2 pi. Okay, typically what we do to show fixed points, that means we're looking for a place where cosine of x equals x. Okay, but if we think cleverly, cosine of x equals x, that's the same as cosine of x minus x equals 0. We just subtract x from both sides. So if we're trying to show cosine of x equals x, if we're trying to show there's a fixed point, we can think about it as showing there's a place where cosine of x minus x equals 0. We're just showing the existence of a 0 for this function here. Okay, and how do we do that? Well, we're looking in this interval here from 0 to 2 pi. So let's see what happens at 0. Cosine of 0 minus 0 is 1 minus 0 is 1. And at the other endpoint, cosine of 2 pi minus 2 pi is 1 minus 2 pi. So that's about equal to 1 minus 6.28, etc., which is about equal to minus 5.28. And so that means at 0, we have that cosine of 0 minus 0 is bigger than 0. The output is 1. It's positive. But cosine of 2 pi minus 2 pi is less than 0. So there is a place between 0 and 2 pi where cosine of c minus c equals 0, i.e. cosine of c equals c. Okay, so there's a point C between 0 and 2 pi. Graphically, if we want to look at it here, we can check this is the cosine function. We can check it against the line y equals x. So this line here, this black line, is all the places y equals x. So here, the cosine function intersects this line at this place, and so the y value and the x value must be the same, i.e. we have a fixed point. Right? If we plug in 0.739 into the cosine function, we get as an output 0.739. Here's another cool application of something you can do with the intermediate value theorem. Take any map you like. Here I have a map of the United States. And draw a circle on this map. You can see I already have a circle here. We can use the intermediate value theorem to show that there must be 2 points that lie on opposite sides of the circle. When I say opposite sides, you know what I mean. Like there's a point here, its opposite is over there. So there must be 2 points on opposite sides of the circle that have the exact same temperature. And here's how we're going to do that. We're going to use the intermediate value theorem, and that means we need to define a function. Okay, so here's the center point of the circle. Okay, pretend that's the center point, that's not exact. For an angle measure x, we're going to let T of x be the temperature of this point here. So you rotate from the horizontal line by x degrees, and we take a look at the temperature at this point on the circumference. So T of x equals temp at the circumference of x degrees, or x radians. So that's T of x. We're going to define a new function called f of x, which is just T of x minus T of x plus pi. Okay, why x plus pi? Well, if we take an angle measure of x radians here, if we add pi radians to it, that's going to give us this point on the opposite side. Okay, we're concerned about points on opposite sides, so we're defining this T of x plus pi. This just tells us the temperature at the opposite side of the circle. And what's cool about this? Well, notice that f of 0 is T of 0 minus T of pi. That's not a surprise. Okay, but also notice f of pi is T of pi minus T of 2 pi. But what does 2 pi radians means? Well, a rotation of 2 pi radians, if we start here and rotate by 2 pi radians, we get right back where we started. So 2 pi radians, that's the same as 0 radians. So f of pi is t of pi minus t of 0, which is notably the negative of f of 0. Right? T of 0 minus t of pi is the same as negative t of pi minus t of 0. Okay, but what do we do with that? Well, there are three possibilities that we can be working with. Either f of 0 equals 0 equals f of pi, in which case t of 0 equals t of pi, and so that means there are points on the opposite side of the circle that have the same temperature. Or f of 0 is bigger than 0, which means that f of pi has to be less than 0, because f of pi is the negative of f of 0. But by the intermediate value theorem, because this f function is continuous, right? And this f function is continuous because temperature varies continuously. If we walk around this circle, the temperature will vary continuously. It's not going to have a sudden jump anywhere. So the t function is continuous, so that means our f function is continuous. So we can use the intermediate value theorem. By the intermediate value theorem, there exists there's a point C in the interval from 0 to pi where f of c equals 0. We're just using the intermediate value theorem to show a 0. If f of c equals 0, then that means t of c equals t of c plus pi. We're looking at the places on the opposite sides of the circle. They're going to have the same temperature. Okay, and the other thing is f of 0 is less than 0, which means that f of pi is bigger than 0, but then same logic. The intermediate value theorem says there's a place on opposite sides of the circle with the same temperature. How neat is that? You draw any circle on any map, you're guaranteed to have 2 points on the opposite sides of the circle that have the same temperature. I think that is super duper cool. And before we leave off, I want to make one quick note. The intermediate value theorem only applies to continuous functions. Okay? Like, let's think about the function f of x equals x divided by absolute value of x. If we remember, its graph looks a little something like this. Okay, it is true that f of minus 1 is minus 1 and f of 1 is 1, but there is no point where the output is 0. Okay, so just be wary of that. We have to be dealing with a continuous function. Okay, so to recap, the intermediate value theorem says a continuous function can't skip values. A very common application of this is to find zeros. We can use the IVT to find zeros, and the way we do that is we show that there's a place where the output is bigger than 0, and we show that there's a place where the output is less than 0. So we show there's a point x equals a where f of a is bigger than 0, and there's a point x equals b where f of b is less than 0. Then there is a C between A and B where f of c equals 0, and that's how we find the zeros. And once we know how to find zeros, we can find fixed points. We use the intermediate value theorem to find fixed points. And the way we do that is we find the zeros of f of x minus x. Okay? And when I say find the zeros, we don't actually find the point itself, but we just show that there exists a point itself, right? In this example here, something like this, we can show that there is a c where f of c equals 0, but we don't necessarily know what the c is, right? If we think back to our very first application of the function, of the intermediate value theorem, we showed that the function sine of x has a point in the interval from 0 to pi over 2, where sine of x equals 0.3, but we weren't able to actually figure out where that point is. We were just able to show that that point exists. But with this, you'll be able to use the intermediate value theorem to find zeros and to find fixed points. Thank you very much.